Okay, buddy. Let's try another problem out here. So this is a tensile test is performed on a specimen of some metal alloy. It's found that a true plastic strain, here, that's a key word, of 0.1 is produced when a true stress of 260 megapascals is applied. For this alloy, the value of the strain hardening exponent is 0.2. That's important for some equations. It says on basis of these data, what true plastic strain will be expected for a total true plastic stress of 340 megapascals. So first off, what is true stress and true strain? So first off, if I solved previous problem, I showed you, well, our stress strain diagram looks something like this. If you know what this means, it means right here we're linear, eventually we're plastic, we get to this point right up here, and eventually it goes back down. And the reason it seems like it goes back down is not because it actually does go back down, because when I'm actually measuring this, what's happening is the following. Initially, I have something that looks like, okay, let me draw it properly. You have something that's tested, which is called a blank. So it looks kind of like this. It's a little dog bone shape. For now, though, I'm only going to focus on this part of it because I don't have to draw that every single time. And so when I have initially, it's like this. I stretch it. It initially stretches. Gets a little bit longer, a little bit thinner. Eventually, though, it will not stretch everywhere at the same time. It'll begin to locally deform. So it'll get longer again, but now it's beginning to get I'm really messing with that. There we go. It's trying to stretch all the middle. And that will continue to get thinner and thinner. If it's very, very ductile, it will get down to a point. If it's not very, very ductile, it will, break a bit earlier. And so it's going to get to a point where it eventually breaks. What you can see here is that I'm no longer changing shape all along the length. I'm only changing at that very, very thin point now. And so that's what's happening up here. So if I'm actually taking into account the fact that this is messing up and my area is drastically changing, and I calculate my stress and strain based on what's going on really, I get a different curve. And so my curve looks something like this. So here's the old one, and here is the new one. So it actually increases all the way until finally it fails. So this is the true curve, and this is what's usually called engineering stress, because I'm not actually taking that into account, because I don't have to worry about it most of the time, because we don't usually go that far. Okay, so with that being said, how do we deal with this? How do we figure out all this stuff, this true stress to strain? Well, we have some equations that help us out here. So I'll give both of them to you. You can look them over. So log of true stress is equal to log of K, there we go, that looks good, make sure I'm doing this right, plus N log of true strain. Okay, that's pretty good there. And then we also have another one for true strain. So true strain is equal to my true stress over K, and this is to the 1 over N. Perfect. As I know this is the same equation, I just rearranged it a little bit. So these are my two ways. I can relate my true stress to my true strain, or my true strain to my true stress. And so this is how we can correct our data from engineering stress to real stress, or vice versa. I know one or the other. So with that being said, we have some things we need to figure out. So things we need to figure out to be able to do this are to figure out, well, one, what is K? That's one of our constants. And two, what is N? Well, N right here is the strain hardening exponent. So that's been given to us. We already know what that value is. K is the only thing we have to be able to calculate to be able to use this relationship. Now, luckily, it gave us one of these situations. It said that we have a true plastic strain of 0.1, we have a true stress of 260. So it means we know one of these, and we can solve this equation right here to figure out K, and then we can plug that back in to figure what our true strain is at the end. So let's try this out. So we have a log of 260 megapascals, okay, is equal to log of K, don't know what that guy is yet, plus 0.2 times log of 0.1. That looks good so far. What I'll get from that is that log k is equal to 2.615. So what is k? Well, I just have to take, make sure I do this right. Yes, I have to take 10 to the 2.615 power, and I get it, which comes out to be 412 megapascals. It's coming out to the same units as this guy. Okay, so we have k, we have n, which means we can go back and find our true strain for our second situation. So it says, what is the true strain when we have a true stress that's equal to 340 megapascals? Well, let's find out. So 340 over 412. I'm leaving off the units because they're the same here, they would cancel. Over 1 over 0.2. Now if I plug that into my calculator, I get that it comes out to be 0.382. These are huge stresses because these are huge strains. Sorry, huge strains because these are huge stresses, and I'm at a point where it's really about to break here. But that's okay. It's good for us to know. So that's it. These are one of those problems where you really just have to plug and chug in the equations because all these guys are. These are ways of us correcting our data. Gives us a good model for it. Beyond that, just know that this k is a constant, which you're calculating. N is the strain hardening exponent. You're going to need at least one case that you know to be able to solve for whatever's given, not given. And you just plug it in and go from there. Thanks for listening. Hopefully this helps you. I'll see you all next time. Bye-bye.